Yeah, yesterday we discussed about some common properties of minerals, and today we are going to discussing about the continuation part of common properties of minerals, how we can identify the mineral, and what are the properties we have to identify in a mineral. Yesterday we see about color, and today we are going to discussing about streak. Yeah, streak, it is also known as a color of the finely powder of a mineral. How we can identify that? Generally, if we can scratch with a knife on a surface of a mineral, sometimes maybe it is the knife maybe it is very sharp, and then we can streak, and again the mineral you can streak on a or a scratch on a streak plate, we'll get some powder. We'll get some powder. So that the hardness we can say about that the hardness of a streak plate, that is around maybe a 7. Sometimes we cannot use it with these minerals. It's above the hardness. The streak, it is a more reliable. It's a very good diagnostic property of color. When you compare with the color, it's a more advantageable. It's a more advantageable and more reliable when you compare with the color property. The streak of a transparent, and it's a transparent of mineral. Whatever mineral we have hold, as per that property, we can identify the mineral. The streak transparent and transparent minerals, it is in white. The streak, it's a dark color of a minerals with a non-metallic luster. It's a lighter, very lighter than the color, but minerals which exhibit the metallic luster and which have a streak darker than the other color. Sometimes maybe it is identified by the appearance of a magnetite, chromite, and it is differentiated by the streak. Sometimes if it is in a black of a black for a magnetite and light brown for a chromite. And next property, it is a luster. It is a nature and amount of a shine which any mirror, it can be offered by the reflected of light and it's a surface. Whatever light, if it is a fall on a surface of a mineral, and the light maybe it's suddenly if it is a reflected, if it is getting the reflecting. As per in that reflecting, will it is showing different types of compositions and different types of reflecting colors. Whatever a mineral, it has a capacity and a mineral surface. As per that, the light, if it is a fall on a mineral surface and a mineral surface, it's immediately it is getting the reflecting. Fundamental luster, it is a two type. One, it is a metallic, and second one, it is a non-metallic. That means the two types of lusters, luster of a mineral property we can able to identify. One, it is a metallic, second one, it is a non-metallic. In a metallic luster, we know that it is it's very brilliant appearance of a metal, such as just we can see look like as a gold, silver, how they will be giving the luster, how they will be reflecting the light very brightly. So there's that property we can say that those minerals are having the metallic luster. Some native metals and the most of the sulfides belongs to the maximum this type of property. Example for pyrite and pyrite associated minerals. And some minerals doesn't show any luster, Such type of property it is called a metallic cluster, non-metallic cluster. These non-metallic cluster lie generally light colored, and their streak may either be colorless or a light color, or several varieties of non-metallic luster we can recognize. Now, if you see, it is a vitreous, adamantine, pearly luster, silky luster, greasy luster, earthy luster. There are various types of lusters available as per mineral properties. Vitreous luster, the luster of a glass, nearly all the silicates, it's exhibit is this luster. Maximum silicate minerals are exhibiting this type of the vitreous luster, like it's a glass like a luster it will be exhibiting. Next one, it is a adamantine, a brilliant luster like that of a diamond. This luster is characteristic of minerals with a refractive indices between the 1.9 and 2.6. The best example for this one, zircon, diamond, and rutile. So here, it's a this luster. It is a look like as a diamond. This luster is a characteristic of minerals which are refractive indices between, that is a 1.9 to 2.6. The best example for this one is zircon, diamond, and rutile. The refractive indices by the combination of yellow or a brown color or a resinous luster, it is produced. It is a luster like of resin like luster we are calling, that is pearly luster. It is the shine of a pearls. This is generally observed on mineral surfaces that are parallel to the cleavage of a planes. That means if you can identify the cleavage planes in any mineral, and then these shiny type of luster, we can identify in a observing of mineral surfaces which are parallel to the cleavages plane. The best example for this one, cleavage surface of a talc. Next one is a silky. The silky, the reflection like that of a silk. It's look like a silk-like a structure. That means, suppose if it is light, if it will fall on a mineral, the silk how it will be appearing with our eye. So similarly to that, the same mineral, it's exhibiting the or reflecting the light. The example for this one, asbestos, gypsum. Another one, it is greasy. It's look like a very tough covered with a thin layer of oil. Whatever oil, if it is, we can able to see like a plug oil. So such type of color or such type of luster, it will be reflecting from a mineral. Earthy appearance. It's look like a dirty earthy appearance. Like the best example for this one, kaolin. The best example for this one, kaolin. Next one, next property, it is a hardness. It's very important in a mineral identification. It is generally we can define the resistance of a mineral, either where we are scratching or abrasion on its surface. Hardness, it's a used as a diagnostic property in the identification of a minerals since the beginning of this systematic mineralogy. We know that the diamond is a very hardest of all the minerals, as it can scratch all others. And the soft one, it is a talc. Soft one, it is a talc. And we can scratch with any of a mineral on this mineral. So that this hardness, it's very low. In 1824, the most scientist here, Australian mineralogist and geologist, he was proposed the scale of a hardness. The scale of hardness, it's 10 types. Yeah, one, it is a talc. That means, suppose if you can scratch, with our nail, if we can scratch with our nail on a uh, talc surface body, easily we'll get the lines and easily we can divide that and we'll get the fine powder from this is a talc. And the talc, it is very useful mineral. It is a useful in it to making of a paste powders. Paste powders. Uh, so the best one, it is a talc. Second one, it is a gypsum mineral. Second one, it is a gypsum. Third one, it is a calcite. Fourth one is a fluorite. Fifth one is a apatite. Sixth one is a orthoclase. Seventh one is a quartz. Eighth one topaz. 9 corundum. 10 is a diamond. This is the hardness of a scale, and some minerals are having the different types of hardness. So as per this hardness, the arrangement will be there. That means, suppose example, if you can see the alumina related or bauxite related material. The bauxite related material we cannot be able to scratch with our nail, and even it is not on a scratch and streak plate also. So this type of minerals, it will become under the nearby the 8 to 9 hardness. So that means the mineral properties. If we can able to identify the mineral properties, definitely we can say. Suppose if we can take the diamond mineral. The diamond mineral we cannot able to scratch. We cannot able to scratch with our naked eye. With our nail or with a chalk or with a streak or whatever it is, streak plate. It doesn't getting any scratch on a surface. It because of it's very hard. The hardness scale, it is a very high. So that the diamond, it has a acquired, it was acquired very high position in a mole harsh, in a Mohs harsh scale. You take any of a mineral and scratch those lower in the scale, and it will be scratched by a higher scale. Definitely. Suppose example for if you can take a diamond and you can scratch with this diamond on quartz and topaz, but we cannot we cannot scratch with a topaz on a diamond surface body. Because of this hardness, it is very high. But when you compare with this hardness of with this one, the topaz hardness, it is very low. The tools for the used in finding the hardness of a mineral, it's very simplest. It's very simplest because of the minerals of a hardness one, it have a greasy feel. We can scratch with a thumbnail and slightly we can we see the little bit of a hardness feeling on a gypsum. That's the second. We know that. And soft pin can scratch on a calcite. Yes, definitely. If you see the calcite, calcite, we can scratch with the using of this pin. On calcite, it is getting the scratching with a pin or a small chalk or whatever it is. But when we see this, sorry. Yeah, when we see this, all these minerals. Oh, either maybe it is you take a good knife with a scratch and appetite, but uh, difficulty it may be scratch on the feldspar because of the hardness. Slowly it is going to be increased. Feldspar means it is a composition of orthoclase. That's a potassium orthoclase or potassium feldspars or whatever it is. So that here slowly the scratchness it is going to be in sorry, the hardness it is going to be increase. So that is the reason we are unable to scratch with thumbnail or a knife. And next property, it is a cleavage and parting. It is very useful in a mineralogical property. Cleavage, it is defined as a tendency of a mineral to cleave or a break. That means here a splitting property. That's a splitting property. The surface, it has some splitting property of planes. The planes, it has some splitting property, and as per that we can divide, as per that we can break, or as per that we can split the surface. It has some directions. According to the directions on a plane surface, we can have a chance to split it. The splitting may take place with varying degrees of easy perfection. Sometimes the cleavage planes are maximum cohesion in a mineral. These directions along which such breakage take place in some minerals, maybe it is one, or while others may two or three. Cleavage, it is said to be perfection as in the micas. Cleavage has a bearing on a crystal structure, and it's a breaking of a mineral between atomic planes as per the directional property. Cleavage, again, it can be described with a reference to the quality and crystallographic directions. The direction it is expressing by the face of a crystal to which cleavage planes are it's a parallel. So suppose again, if you go into the back of a crystal system, as per the crystal system, the cleavage planes are as per the crystal system, the axis, how they are how they are moving, or how they are transporting through the center of axis. According to that, the cubic, it has a 001 Miller index, it is showing. Octahedron, it is showing the 111, and prismatic, it's showing the 110. And only crystalline substances, it's possess this property, where amorphous substances lack in cleavage. How we can do the parting? In the parting, this feature is very similar to the cleavage. The parting result due to the weakness produced by the pressure or twinning, it can be considered as a false cleavage. The parting is not exhibited by all substances, but only by those who are twinned, subjected to the proper pressure. According to this is pressure where we need the parting, and that means where it is where it has a weakness and it's produced by the pressure or twin. There definitely it has some breaking point, and there we should have a chance to break the mineral. And then parting, it's a result from stress in operation, either during or after formation. Example for basal parting of pyroxene minerals. And another property, it is a fracture. Fracture means it's a breaking property. It's a breaking in a direction other than cleavage plane. A little bit of it is a cleavage only, just a small small scratches or small breaking lines on a plane, but it is a major, little bit, it is a major breaking line within a mineral. It's a different from the cleavage and in being irregular, curved and uneven, and that's not to confined to any crystallographic directions. The common types of fractures are even, uneven. There are four types we will see. That's the first one, it is even. Second one, it is uneven. Third one, it is splintery. Fourth one is a hackly. Fourth one, it is a hackly. And fifth one is a concordial. And sixth one is a earthy. So first we see the, first we see this fracture type, even. If the nature of the broken surface is a flat and smooth, it is called as an even fracture. So here what is happening, if the nature of the broken surface is it's a flat and a smooth. If it is look like a flat and smooth, it is called even fracture. The example for this one, it is a chet. And next one is uneven. If the surface it is entirely irregular and rough, it may many of minerals exhibit it is uneven fractures. Example for quartz. And splintery. If breaks takes place in a minute, the threads are needle-like form. It is called as a splintery clearance. Example for this one, tremolite. And another one, it is hacking. This type of the fracture, when we see the highly irregular broken surfaces and which develop the needles like projections on a sharp points. Example for this one, native copper. And another one, it is a concordial. In a concordial fracture, it is produced when minerals like quartz are broken. The fractured surface has a number of curvatures, both concave and convex. That means here the fracture of surfaces we can able to see, that is in a two types of structures, that is in concave and convex type. The fracture is known as a shell-like structure, or it's known as a shell-like. If such features are very distinctive them to the subconcordial, it may be used. At the when the broken surface is very smooth and soft. Example for chalk. The tenacity. The another property, it is tenacity. The force or a strength which keeps the particular mineral to resist. Such maybe it is a crushing, bending, breaking, or tearing. It is called as a tenacity. That means whatever pressure we are applying on a mineral, and as per that, the mineral it is going to be bent, or it has a chance to do the crush. The mineral it has a rest to able all these things. The various items or various terms used to describe the tenacity of a mineral are as follows: brittle, ductile, flexible, elastic, and malleable. A mineral, first we come into the brittle. A mineral which is breaks very easily to grain or a powder. Or when you come into the ductile, in a ductile property, it shows a smooth surface. And when it's cut by a knife, the example for this one, kaolin or a talc. Or flexible. A flexible property which can yield bending or a stress, and the remain bent, it is a flexible. The example for this one, it is a asbestos. Next one is elastic. When a mineral yields to stress and region its original shape on the release of a pressure, Example for this one is the plate of white mica. It has a elastic property. If you can apply the stress or a pressure, and again it's regain the original shape. And really on the release of the pressure, when we are using the pressure or a stress on a particular mineral, and slowly it is going to be changed their original formation. And if you can release that pressure, if you can remove that pressure, and it is getting the original shape. The best example for this one is white mica. Final one, it is a malleable. If a mineral, if it is a flattened or deformed without any breaking under a hammer, then it is called malleable. The example for native gold, and iron, it is also. Form under structure. Yeah, in a form under structure, forms. The external geometrical shape, it is a reflection of a internal arrangement of a atoms. Such shape, it is called as a form. Forms are three types. There are three types of forms we can see. One, it is crystallized. If a mineral develops well-defined shape, and occurs, it occurs is like a perfect crystal. If you see, that is like a perfect crystal. And second one is a crystalline. In a crystalline, if a mineral does not bear a regular shape, but indications of a crystallization are visible by the presence of a small grains, where in fact each grain is a small crystal by itself. If you see in a amorphous, this is a third property of forms. If mineral lacks regular shapes as well as internal atomic structure, which means the formation has not undergone the process of crystallization. That means directly it is going to be formed without any shape, maybe without any change of atomic structure. We see the quartz occurs a perfect crystals when it is crystallized in a crystalline state. Or if you see the ordinary glass or opal occurs in amorphous bodies. Next, coming to the structure. In a structure, many times minerals which are exhibiting the definite shape externally, which is termed as a structure. That means the externally how it was arranged, the shape how it is look like. The structures are very characteristics in some minerals. Minerals many occur individually, it's being the independent themselves in a groups or aggregation. The following types we will see. One, it is a acicular. When in acicular, when a mineral is made up of a very sharp and slender needles. The best example for this one, it is a natrolite. Second one, it is a capillary. In a capillary, means it's a small needle-like structure or a hair-like structure. The mineral, it has a hair-like structure. It is on the example for this one, it's a millerite. Bladed type. In a bladed type, when it's aggregating the thin blade-like sheet, it's a blade-like sheet. The parts we can see. This is an example for this one, kyanite. And another one is reticulated. In a reticulated, if the groups of slender crystals are many lattice shape, so that may be such as a rutile needleness in some micas, radiated or divergent. When fibers are needleless divergent from a central part, dendrite is look like as a tree-like a structure. Tree branches, how it is look like, or neurons. If you see in neurons, the structure how it is look like. The same structure will be appearing. It's appearing druzy. In a druzy, when the surface is covered with a layer of a different mixture of crystals. The example for this one, quartz. Columnar. In a columnar joints, the aggregating of a thin or a stout parallel columns. It's an example for this is tourmaline. Laminar or tabular structure. In a lamellar or tabular structure, when a mineral is made up of an aggregate of plates, one over the another, the plates are separable. Example for this one, chlorite. And fibrous type of structure. It is made of different fibers and which are all arranged parallel to the one to another. Example for this one, it's asbestos and gypsum. Granular structure, foliated and mammillary structure, globular structure, portodile, oolitic, reniform, banded. These are all the various types of structures will be identifying in different minerals. The best example for one, reniform, it's important. It is a reniform, it's a shape of a kidney type of structure. It is, we can able to see in a hematite. Oolitic structure, it has a small spears like structure. It's a we can able to see this in siliceous oolite. And also amygdala structures also there. These amygdala structures we can see in a geolite infillings, cavities of lavas, and the stellite structure. The stellite structure we will see in a wavellite. And wiry, these wiry mean it's forming like as a wires. It's a forming like as a wires. It is we see in a copper material. Yeah, pseudomorphism. We come into the there are three types of morphisms we can able to see in the formations. Those three are: one, it is a pseudomorphism; second one, it is a polymorphism; third one is isomorphism. Yeah, it's a pseudomorphism. The external forms, whatever it has, it's a different from a mineral. When we are compared with the total chemical composition, that means if you take a granite composition example for one, here there are various types of minerals for there in that one. Example for the main minerals are quartz, feldspar, silica. That means the quartz only. Biotite, biotites, and sometimes it's may having the other radioactive type of minerals. Finally, we see here the composition. It is different chemical compositions will be there in a one rock. This type of a formation, it is called as a pseudomorph. And this it is a replacement by the one mineral by the another without any disturbing the within a shape. Such replacements are called as pseudomorphs. They are formed in the gradual change in a chemical composition by the alteration, or sometimes maybe it is a replacement by the original particles. And a new mineral, it's occupying the cavities, and by the deposition of one mineral on the other. The polymorphism. We see in a polymorphism, the phenomena, if it is see by the definite chemical composition, it may appear in a different formation. The physical properties also, if you can see, it's exhibiting in a different physical properties. It is in a crystalline formation, or sometimes maybe it is in a we can see in a two substances of formation. Example for CaCO3. If you see the CaCO3, we can it has a calcite crystalliting in a hexagonal system, or it is in a aragonite crystalliting orthorhombic system. You see here, aragonite is also having the same composition, and calcite is also having the same chemical composition. It's a calcium oxide, that is a CaCO3. But if you see that is a if you see that is a crystallization part, that is it's a hexagonal system. In a aragonite, that is indicating the crystallizing in an orthorhombic system. So this type of the chemical body, it's a dimorphic. That means two morphism, two types of morphological features it has. So like that, there are three forms or substances. We see that's a TiO2, it's a rutile, octahedrite, and brookite. And it's a substance, it is known as a trimorphic. It's known as a trimorphic. That means the three types of the forms that we can able to identify in that one. Next one, it is an isomorphism. The isomorphism, it is the word, it was a derived from the Greek. The isos means it's the same, morph means in a shape or a form. The word, it was introduced in 1819 by the Michelet. Isomorphism, it is a feature by virtue of which substances with analogous or allied the chemical composition can crystallize in closely related to the crystalline form. The calcite, dolomite, and magnesite are isomorphous. But as per the chemical composition, if you can see that is a dolomite, it is a CaMgCO3, and the calcite, it is showing the CaCO3. The albite and anorthite are isomorphous, and their solid solutions will give a rise to plesioklase series. The members of crystalline in a triclinic system, in such series, one element is replaces the another, or one atom by another, which are having the atomic radius, it is similar. The another most property, it is the specific gravity. The specific gravity, it's a mineral ratio to weight, and that equal volume of water at 4 degrees centigrade. We will take as a, or we will consider as a unit. The mineral, it's having the specific gravity of 3 weights, 3 times that of same volume of your water. When a body, it is weight in water, it's a loss spot of its weight. The loss of a weight is equal to the weight of equal volume of your water, whatever it is losing. And the weight we will see in a mineral. Sometimes maybe it is air presumed as a W1, that in a as the water W2. And the loss of the weight, how we can find out, that is a W1 minus W2. Then the specific gravity. The specific gravity of a mineral we can identify with this one, that is a W1 by W1 minus W2. This is heavy for a mineral consisting heavier, and it's a closely spaced atoms where it is arranged. The specific gravity of most of the rock forming minerals between the 2.53 to 3.0, except fun for a pyroxenes, it's slightly more than, sometimes it has a 3. For most of the iron ores, it's ranging between the 4 to 5. And maximum it's more than 7 if you see in a tungsten ores. Yeah, from this one, in a specific gravity, the most important we are using the Jolly's spring balance for small samples. And second one, it is a Walker's steel yard for long specimens and heavy liquids and heavy liquids and chemical balances. Here it was mentioned the Jolly spring balance. In a Jolly spring balance, the method which is employing the balance based, it's a Archimedes principle. It was involved here, and which consisting of a vertical stand and adjustable base. You see here, it's a adjustable base. It was attached with a gradiated scale, and along with a mirror. A spring in a vertical suspension against the scale. It is also provided from top screw at the lower end of the which there are two scale pans in a vertical fashion, one below the other, to find out the specific gravity. A fragment of a given mineral is placed upper pan, and the elongation of a spring with a reference to its bottom point, it is measured according to the gradiated scale, and it's a proportional to the weight of the mineral in a air, that is a WA, and the mineral, it is a transferred lower pan and fully immersed in a water, and there we can see the proportional again the weight between the in a mineral. So finally, we will get the principle, that is a specific gravity. It is equal WA by WA minus WB. We will get the final result with this one. Yeah, again, Walker's steel yard it will also there, but and one more, that is the specific gravity of Walker steel yard. We may find out that is a specific gravity. It is called 1 by m. By 1 by m minus 1 by n, it is equal. We cancel all the ones, and then finally it is remaining the n by n minus m. And another one, it is a pinometer. This is used to find out the specific gravity of a small piece of minerals. Maybe it is as a liquid. It's a small glass bottle with a ground glass stopper. There is a very fine opening through stopper. It will be there. Now let the weight the bottle under the dry empty conditions. That will be a W1, and the weight of the pinometer with the use of fragments, so noted W2, that is. Then the bottle is partially filled by the pure water and boiled sometimes to drive out the air bubbles, if any, through the capillary openings in the stopper, or some or more water it is going to be added with the bottle. And finally, when it's getting the cooled, then the weight it is noted, that is a W3. So that we will get the values here of the specific gravity, that what we have noted previously. That's a W2, W1, W3, and 4. The principle it is indicating as a W2 minus W1 by W4 plus C into W 2 minus W1 minus W3, where the W2 minus W1 is the weight of a sample, and W3 it is a pinometer with the sample fragments and water it is indicating. And again, W4 plus W2 minus W1 or W3, which stands for weight of the displaced sample. So that we take must and should care taken to drive out the entire air. Otherwise, it would result in a serious error. However, it is not desirable to use the bottle determination of specific gravity unless the technique it is not available. And most of the cases we see it is to find out the liquid like a hydrogen material, bromide, such type of material, minerals weight we can able to identify with this one. Heavy liquids. This is useful for only to find out these liquids. Two liquids which are generally used for methylene iodide or bromoform, which are visible with a stone. When mineral grain it is introduced into the known liquid, it's a known into the liquid. If it is floats in the floats in the end of that mineral, it's a mineral has got a less specific gravity than the liquid. Some of the rare properties we see in a minerals. These properties are not seen in all the minerals. Only just a few cases, only few minerals are having these type of special properties in a particular minerals. Certain properties are limited to variety of minerals, which includes the phosphorescence, fluorescence, visibility, magnetism, electricity, and etc. properties. Phosphorence. What is a phosphorence? Very few minerals which are emit the light, they undergone heating, rubbing, or whatever. That means if you're getting the pressure on a surface of a body, or if you're getting the heat on a surface of a body, or if you're getting the light on a surface of a body, then it is showing the different property. Even on exposure of electrical radiation, certain minerals which are exhibiting this property, diamond, chloride, display phosphorus under varied conditions. Diamond and exposure to under sun, it's become a phosphorescent property. It is showing. So phosphorence means it's absorbing and releasing the energy in different colors. Whenever the sunlight, if it fall on the one, immediately it is reflecting. Immediately it will be reflecting. In different colors, it is reflecting. Or else when you go into the fluorescence, it is well displayed by the mineral fluorospar. It's known as fluorescence. It's a fluorescence. We can suppose the fluorescent minerals. It's absorbing the light. It's absorbing the light, and if you the same light we can able to we see in a dark nights or in a dark color areas. Suppose if you see the fluorite, you keep in a dark light or you can keep in a dark places. It's showing the violet color or it is exhibiting the violet races. Or again, if you see the scheelite, it's also one mineral, and you can keep in a dark place, and it's also exhibiting the blue color of the light. That means the original property it is emitting. The original property it is emitting. So that these type of properties we need to see, and feasibility we will also there. The feasibility it's on heating of various minerals behave in different ways. Some are fused very easily, even in a candle flame. It's a stibnite or quartz in infeasible.
and Borknoll has suggested the feasibility of a scale that it is as follows. Stibnite is 1, chalcopyrite 2, almandine 3, actinolite 4, orthoclase 5, enstatite is 6. A mineral which is a good conductor, it's fused with more difficulty in a blowpipe flame than a poor conductor with the same melting point. As the former transfers the heat rapidly, it is other parts. It's spreading into the other part very quickly, and it reaches the melting temperatures very late relation with to other. Here, magnetism. The magnetype of minerals, it has a magnetism property. It's a maximum you can able to see this property in iron ores, and another one it is a electricity property. In some minerals which are having the electricity property, it's when we giving the heat. When we giving the heat, or when we give the pressure on a mineral, it has a capability to produce the electricity. Tourmaline and quartz, it's belong to the first two type. First type where they are known pyroelectric, and the latter piezoelectric, which was the first detected in quartz in 1881 by the Peary. And it's also known by the very close the first word war sound waves that are produced by the submarine, and it can be detected by the piezometric current, and it's applying by the quartz. Okay, I'm stopping here.